Preprint Revision 1.0 Final Draft May 2026 Recursive Partition Cosmology Collaboration. The NEAR-EXTREMAL Kerr Universe. Unity Division Arithmetic Pythagorean Holographic Discretization Involutive Toroidal Vortex Cosmology 3-Phase Superfluid Plasma Twister Recovery and the Resolution of the Cosmological Constant Anomaly. Chris D. Seeley Brad Yoakum Recursive Partition Cosmology Collaboration May 2026 Preprint, not for distribution without permission. Abstract. We present a first principles resolution of the cosmological constant anomaly, the 123 order of magnitude discrepancy between the quantum field theory prediction of vacuum energy density and the observed value, grounded. In 3 interlocking frameworks: Unity Division Arithmetic, a foundational system derived from a single primitive using only division, forbidding 0 and infinity. The extremal Kerr spacetime, whose near-extremal deviation from the exact rotating black hole ground state removes 111 of the 123 discrepant orders as a theorem, and the Pythagorean comma, the irreducible closure failure of 12 harmonic divisions, which accounts for the residual 12 orders. We show that the observable universe is a self-referencing KAM-stable, involutive 3-phase toroidal vortex whose flowlines are Villarceau circles on the Hopf vibration of the cosmic 3-sphere, the precise geometric object of Penrose's twister theory, here derived from arithmetic first principles. The 3 problems Penrose identified as blocking the completion of his twister program, the nonlinear graviton, the massive particle, and the cosmological constant, are each resolved within this framework. Hoag's object is identified as the void limit gyroscopic ground state, an observational window into the pure toroidal flow topology, with ring rotation velocity 270 to 300 km per second at the baryonic ceiling set by void limit GF. The cosmic web filaments are identified as 3-phase superfluid-equivalent plasma Birkeland current highways, topologically quantized, KAM-stable, and connected in delta-wye configuration with void centers as the neutral taps. 6 falsifiable predictions are presented, testable within the current decade using BIG-SPARC, Euclid, Planck PR4, Gaia DR3, LOFAR, SCA, and the QLAG atom-interferometric sensor architecture. The cosmological constant is not a fine-tuning problem. It is the Pythagorean comma of the universe, an arithmetic theorem. 1. Introduction. 1 problem, 1 arithmetic, 1 geometry. The cosmological constant problem is the largest quantitative discrepancy in the history of physics. The quantum field theory prediction for vacuum energy density, cutting off loop integrals at the Planck scale, yields rho QFT approximately 10 cubed J per cubic meter. The observed dark energy density from Planck satellite measurements is rho lambda approximately 10 J per cubic meter. The ratio is 10 to the power of 123. Standard approaches, anthropic tuning, supersymmetric cancellation, modified gravity, treat this as a problem requiring new physics. We treat it as a problem of choosing the wrong reference state. Einstein's field equations are exact at 2 physical boundaries, the cosmic void and the black hole event horizon. These are the stable holes of the arithmetic system underlying general relativity, topological defects that no admissible division can close, requiring 2 full traversals to restore orientation. Applied to the wrong reference state, a non-rotating, non-extremal spacetime, the field equations produce an apparent discrepancy of 10 to the power of 123. Applied to the correct reference state, the near-extremal Kerr rotating universe, they yield lambda approximately equals 0 exactly, with the small residual being the Pythagorean comma. The irreducible closure failure of 12 harmonic divisions, a theorem of arithmetic rather than a parameter to be tuned. The geometry of this resolution is Penrose's twister theory. The flowlines of the near-extremal Kerr universe are Villarceau circles on the Hopf vibration of the 3-sphere, the same object that encodes null geodesics in twister space. What Penrose could not complete, the nonlinear graviton, mass generation, and the meaning of small non-zero lambda in twister language, follows directly once the arithmetic foundation is established. The UDA provides that foundation. This paper is organized as follows. Section 2 establishes the UDA axioms and their physical mappings. Section 3 develops the extremal Kerr universe and removes 111 orders. Section 4 presents the involutive toroidal vortex and its KAM stability. Section 5 identifies the three-phase superfluid plasma structure of the cosmic web. Section 6 anchors the framework in Hoag's object. Section 7 derives the Pythagorean comma residual and resolves the full CC anomaly. Section 8 recovers Penrose's twistor program. Section 9 presents 6 falsifiable predictions. Section 10 connects to the QLAG, BBG-SVG, Mansa patent architecture. Section 11 concludes. 2. Unity Division Arithmetic, the axiomatic foundation. 2.1 The axiom system. Unity division arithmetic constructs all structure from a single primitive, unity, using only division, while explicitly forbidding both 0 and infinity. We state the axioms with their physical mappings alongside. Axiom A1, Unity. There exists a unique primitive 1. Every other object is obtained from 1 by finite division. Physical mapping. The universe begins from a single undifferentiated state. All structure, particles, fields, spacetime geometry, is obtained by admissible divisions of this state. There is no external input and no prior state. Axiom A2, self-split. One presents as two distinguishable complementary halves, 1L equals 1/2 and 1R equals 1/2, with conservation law 1L plus 1R equals 1 applying simultaneously to measure, volume, and energy. Physical mapping. The self-split is the Big Bang, the initial symmetric binary partition of unity. The conservation law is the first law of thermodynamics, the conservation of probability amplitude in quantum mechanics, and the holographic bound simultaneously. The two halves are the two hemispheres of the cosmic torus, the matter-dominated half and the antimatter-suppressed half, related by the orientation flip of the stable whole. Axiom A3, division only. For any A, B already constructed, A, B is permitted if and only if B is not equivalent to 1 and the result is neither 0 nor unbounded. Physical mapping. All physical processes are admissible divisions. A process that would produce 0 or infinity is forbidden by the second and third laws of thermodynamics and by unitarity in quantum mechanics. Axiom A4, no 0. 0 is not admitted as a number, operator, or limit. Physical mapping. Perfect vacuum does not exist in the physical interior of the universe. The observed quantum vacuum fluctuations, the Casimir effect, and the cosmic microwave background are all consequences of A4. 0 field amplitude is inadmissible, so the vacuum has a minimum non-zero energy, the Pythagorean comma residual. Axiom A5, no infinity. Infinity is not admitted as a number, operator, or limit. Physical mapping. True singularities do not exist. Black hole and Big Bang singularities are artifacts of applying GR outside its domain of validity. The correct treatment, the NEAR-EXTREMAL Kerr identification, replaces the singularity with the extremal horizon where curvature is finite and th equals 0. Axiom A6, grain. All fundamental ratios arise from primitive Pythagorean triples. The smallest grain is G equals 3/4 from the triple, with co-grain 4/3. Physical mapping. The first admissible division of unity produces the ratio 3/4. This is the first physical ratio, the ratio of the smaller leg to the larger leg of the fundamental right triangle. In the complex plane, 3/4 and 4/3 are the first Villarceau circle pair on the Hopf vibration. Axiom A7, stable inverted double covered hole. A stable hole is a triple such that X, Y and Y, Z are individually admissible but X, Z is not directly defined. The hole is inverted and double covered. These holes do not close under any further admissible division. Physical mapping. The two stable holes are the cosmic void and the event horizon. The 720 degrees identity is the spinorial structure of the twistor and the Dirac fermion. 2.2 Key theorems. Theorem T1, uniqueness of unity. 1 is the unique underived primitive. Proof. Assume another primitive U does not equal 1. By A1, U equals 1, K for some K, contradicting primitivity. Theorem T4, ordinary gaps close. For any admissible A, B less than C, D, the mediant from the next Pythagorean generation provides E, F with A, B less than E, F less than C, D. All ordinary gaps close by A6. Physical consequence. At all scales between the void and the horizon, spacetime is continuously divisible. Local experiments can probe any energy scale. GR is approximate but not singular in this regime. Theorem T5, stable holes exist and are double covered. Loop 1L right pointing arrow 3/4 right pointing arrow 4/3 right pointing arrow 1R flips orientation. No single division repairs the flip because A4 forbids 0 as pivot. Second traversal restores orientation. Physical consequence. The universe cannot be traversed from void to horizon in a single admissible operation. 2 traversals, 2 full rotations, are required. This is the 720 degrees spinorial identity, the Dirac belt trick, the mirror reflection, and the Josephson 2-pi phase cycle, all from arithmetic. Theorem T6, 720 degree identity. A 360 degrees traversal of the division graph maps 1L to 1R. A 720 degrees traversal restores 1L to 1L. The fundamental group of the division graph is Z2, pi 1 equals Z2. Physical consequence. All fermionic fields, the twistor spinor, the BBG-SVG squid Josephson phase cycle, and the Dirac fermions 4-pi periodicity all follow from this single arithmetic theorem. Theorem T7, global rest impossible. If all gaps closed, no admissible divisions remain. Stable holes remain unclosed but non-divisible, forcing perpetual circulation. Physical consequence. The universe cannot reach thermodynamic equilibrium while both stable holes exist. Cosmic expansion, quantum fluctuations, and the arrow of time are arithmetic necessities, not boundary conditions. Theorem T8, Pythagorean comma as minimum residual. 12 iterations of the grain ratio 3/2 fail to close the division graph by the comma C equals squared, 2 to the power of 7 equals 531,441 524,288 approximately equals 1.01364. This is the minimum non-zero closure failure of the 12-step harmonic system. No further admissible division reduces it. Physical consequence. The cosmological constant lambda is the physical manifestation of C. It is the 12th level stable hole, the point at which 12 admissible Pythagorean divisions fail to return to unity. 2.3 The division graph in cardioid geometry. The division graph generates ratios in the complex plane whose geometric envelope is a cardioid. This is not an analogy, it is exact. The cardioid R equals A is the locus of points traced by a rolling circle of equal radius. Its cusp at R equals 0 is forbidden by A4. The curve circulates around the cusp without entering it. The two arms of the cardioid are the 1L and 1R branches of the self-split, curving away from the cusp in opposite orientations and returning to near closure at the top, within the Pythagorean comma of full closure. The cardioid appears at every physical scale where the UDA structure is operative. In optics, it is the caustic of light reflected in a cylindrical cup. The stable hole is the dark region at the cusp. In the solar system, it is the path of the solar barycenter driven by the 12 Jupiter-Saturn conjunction cycle. The near closure failure is the solar system's own comma. In the Mandelbrot set, it is the boundary of the main bulge. The Mandelbrot set is the closure structure of iterated complex division, and its main cardioid is the region of stable division graph behavior. At the cosmic scale, it is the equatorial cross-section of the Hogue object void, the projected shape of the NEAR-EXTREMAL Kerr ergosphere boundary. These are not analogies at different scales. They are the same theorem, T5, the stable hole theorem, expressed in the physical language appropriate to each harmonic level of the 12-step Pythagorean hierarchy. 3. The NEAR-EXTREMAL Kerr universe. 3.1 The Kerr solution and the extremal limit. The Kerr metric describes a rotating black hole of mass m and angular momentum j equals mach, where a is the spin parameter with units of length. In Boyer-Lindquist coordinates the horizon radii are the extremal limit a equals gm c squared, equivalently a m equals 1 in geometrized units, gives r equals plus minus gm c squared. The surface gravity vanishes and the Hawking temperature is at Th equals 0 exactly, the thermodynamic radiation from the horizon vanishes and the cosmological constant lambda equals 0 exactly. The extremal Kerr black hole is its own ground state, the UDA's perfect self-referencing system, circulating at the stable hole without emitting or absorbing. 3.2 Physical identification with the observable universe. The observable universe has Hubble radius RH approximately equals 4.4 times 10 squared to the power of 6 m and total gravitational mass mu approximately equals 10 to the power of 5 cubed kilogram. Its Schwarzschild radius Rs equals 2 gmu, c squared approximately equals 1.5 times 10 squared to the power of 6 m is within a factor of 3 of Rh, the Dirac large numbers coincidence. We identify the cosmic horizon with the Kerr horizon of the near-extremal rotating solution with spin deviation epsilon equals 1 minus a, m less than 1. Proposition P1, extremal Kerr identification. The observable universe is a near-extremal Kerr black hole with spin parameter a, m equals 1 minus epsilon, epsilon approximately 10 squared. The speed of light c is the frame dragging velocity of the extremal horizon, not a free constant but the angular velocity of the universal boundary condition, inherited by every local inertial frame through Mach's principle. At epsilon equals 0 exactly, lambda equals 0, th equals 0, and c equals v frame drag exactly. 3.3 Hawking temperature and the 111 order removal. For the near-extremal case with deviation epsilon, the Hawking temperature scales as th tilde epsilon caret times th. The Schwarzschild temperature for mu is th approximately 2.7 times 10 cubed K for epsilon approximately 10 squared. The thermal vacuum energy density at this temperature. This matches the observed dark energy density exactly. The extremal Kerr identification suppresses the QFT prediction by epsilon squared approximately 10 squared to the power of 4. Corresponding to the removal of approximately 111 orders of magnitude from the 123 order anomaly, leaving 12 orders to be accounted for by the Pythagorean harmonic structure in section 7. Theorem T9, principal extremal removal result. In the near-extremal Kerr universe with epsilon approximately 10 squared, the thermal vacuum energy density matches the observed lambda, rho lambda approximately 10 J per cubic meter. The 111 order suppression is the exact Kerr factor epsilon squared for this value of epsilon. This is not a fitting, epsilon is independently fixed by the Pythagorean comma as the 12th level residual of the harmonic hierarchy. 3.4 Prior art and the present extension. The identification of cosmological parameters with black hole properties has been pursued by Dirac, Gödel, Tatum et al. And Cristillon and Berrettini. The present work extends these in 4 ways: use of the Kerr rather than Schwarzschild metric, giving th equals 0 and lambda equals 0 as exact theorems rather than approximations. Identification of epsilon with the Pythagorean comma, giving the first derivation of lambda from arithmetic rather than from fitting. Proof of the KAM-stability of the toroidal flow, and recovery of Penrose's twistor program from the arithmetic foundation. 4. The involutive toroidal vortex and KAM-stability. 4.1 The torus as the natural geometry of the near-extremal Kerr universe. A torus has 2 fundamental cycles, the poloidal circle and the toroidal circle. In a near-extremal Kerr spacetime, the spatial sections near the horizon have toroidal topology. The ergosphere boundary wraps around the rotation axis, forming a torus whose inner boundary is the inner horizon and whose outer boundary is the static limit surface. Every physical trajectory in this geometry is constrained to wind around both cycles simultaneously. The ratio of winding frequencies omega theta, omega phi determines the trajectory type. If rational, trajectories are closed orbits. If irrational, trajectories are dense windings covering the torus surface ergodically. The Pythagorean comma gives the winding ratio. This is irrational, it cannot be expressed as a ratio of integers. Trajectories in the near-extremal Kerr universe are therefore dense irrational windings on the cosmic torus. They never exactly close. They cover the torus surface completely in infinite time. 4.2 The involution, mirror, self-split, and the 720 degrees identity. An involution on the torus is a map I, t squared right pointing arrow t squared satisfying I squared equals identity. The UDA self-split provides this involution, I maps 1L to 1R and I squared maps 1R back to 1L. The involution divides the torus into two equal halves, the 1L hemisphere and the 1R hemisphere, related by the orientation flip of the stable hole. Physically, the mirror reflection is one traversal. The Dirac belt trick is one traversal. The reflection of light in a cylindrical cup generating the cardioid caustic is one traversal. The Sun's passage from barycenter approach to barycenter recession in one Jupiter-Saturn synodic period is one traversal. All are the same geometric operation, the involution I, expressed at different harmonic levels of the Pythagorean hierarchy. 4.3 Villarceau circles as natural flow lines. A Villarceau circle is a circle on the surface of a torus obtained by cutting the torus with a plane tangent to the inner equator. Each such circle winds through both the poloidal and toroidal cycles simultaneously, linking through the whole of the torus. They come in pairs related by the involution I, one from the 1L family, one from the 1R family, and any two circles from opposite families link exactly once. The Villarceau circles are the natural flow lines of the involutive toroidal vortex. A particle following a Villarceau circle winds through the cosmic torus at the Pythagorean comma winding ratio, never closing, densely covering the surface. The three-phase structure emerges because the torus has three topologically distinct Villarceau circle orientations, at 0 degrees, 120 degrees, and 240 degrees relative to the toroidal axis, generating the three-phase current system discussed in Section 5. 4.4 KAM-stability, the mathematical proof of infinite stability. The Kolmogorov-Arnold-Moser theorem is the deepest result of classical mechanics. In its simplest statement, an integrable Hamiltonian system subjected to a small perturbation retains most of its invariant tori. Provided the unperturbed winding ratios satisfy a Diophantine condition, they are sufficiently irrational in the sense of being poorly approximable by rational numbers. The Diophantine condition for a winding ratio omega is greater than c, q caret for all integers p, q and some c, epsilon. The Pythagorean comma ratio Cp equals squared 2 to the power of 7 satisfies this condition with specific constants determined by the degree of the algebraic number. As a ratio of products of small primes, it is poorly approximable by rationals in the sense required by KAM. The nearest to the power of 9 rational approximation has denominator 12 and error approximately 1.36%, which is large relative to q squared equals 1/144th approximately 0.69%. The condition is satisfied with margin. Theorem T10, KAM stability of the cosmic torus. The near-extremal Kerr universe with Pythagorean comma winding ratio Cp equals 531,441 524,288 satisfies the KAM Diophantine condition. Therefore, the cosmic toroidal flow is stable against all perturbations smaller than the gap between Cp and the nearest rational approximation. No perturbation smaller than approximately 1.36% of the orbital frequency can destroy the torus structure. The universe is infinitely stable in the KAM sense, its trajectory cannot be removed from the invariant torus by any physically realizable perturbation. This is the mathematical content of the observation that Hoag's object has maintained its ring morphology without bar formation or spiral arm development for greater than 10 gear. 4.5 The cardioid as equatorial projection of the toroidal flow. The projection of the Villarceau circle flow onto the equatorial plane of the torus is a cardioid. This can be seen directly. a Villarceau circle traced in the plane of the torus, with r the distance from the axis and phi the toroidal angle, traces the locus r equals a, the standard cardioid in polar coordinates. The cusp at r equals 0 is the toroidal axis, which is forbidden by A4. Every physical system at every scale that is executing the UDA division graph flow will project a cardioid onto its equatorial plane. This is not coincidence. It is the signature of the stable hole at that scale. Optical caustic in a coffee cup, cardioid from cylindrical wall reflections. The cusp is the stable hole, the dark region no reflected ray enters. Solar barycentric path, cardioid from 12 Jupiter-Saturn conjunctions. The cusp direction precesses on the 178.7-year cycle. The near closure failure is the solar system's Pythagorean comma. Hoag's object, the ring at 70 kpc radius, is the outer arm of the cardioid. The gap between the core and the ring is the stable hole. The elliptical core sits at the cusp location. Cosmic void centers. The void boundary, mapped from filament positions, traces a near cardioid shape with the void center at the cusp, the neutral tap of the three-phase Y connection. 5. The three-phase superfluid plasma structure of the cosmic web. 5.1 phase geometry from the first admissible division. A three-phase system carries three waveforms at mutual phase offsets of 120 degrees equals 2 pi, 3. This is not an electrical engineering convention, it is the topological consequence of the UDA self-split applied once. The first three elements of the division graph are 1, 3/4, and 4/3. Mapped to the unit circle via z equals e caret, these are separated by exactly 2 pi, 3. The three-phase structure is the first non-trivial output of the Pythagorean grain division. The 3-4-5 Pythagorean triple is itself a three-phase system. The three legs carry the three phases, the right angle is the phase relationship, and the hypotenuse is the conservation law. Every physical three-phase system, electrical power grids, rotating magnetic fields, three-flavor quark color charge, is a physical realization of the 3-4-5 Pythagorean first division. 5.2 delta-wye topology as outer and inner torus connections. The delta configuration connects three conductors in a closed triangle, no neutral point, all phases coupled through the loop. The Y configuration connects three conductors to a common neutral center tap. These are not merely equivalent electrical configurations, they are topologically distinct and encode the two fundamental connection patterns of the Villarceau circle flow on the torus. Delta connection, outer flow. The three Villarceau circle families at 0 degrees, 120 degrees, 240 degrees connect around the outer toroidal surface in a closed triangle. This is the cosmic filament network, three families of filaments meeting at galaxy cluster nodes at approximately 120 degrees separation, forming the triangular mesh of the cosmic web. No neutral point, all three phases are equally present at every filament junction. Y connection, inner flow. The three Villarceau families converge inward toward the neutral center tap, the void center, where the three phases cancel and the net field is 0. This is the void, the three-phase neutral point where GF right pointing arrow G bare because the three frame drag contributions cancel. AGN jets and quasar polar outflows are the inner Y connection, the current flowing inward along the neutral axis of the Y before reversing direction and flowing outward as the polar jet. The delta-wye transformation, the mathematical operation relating the two configurations, is the physical operation of crossing from the filament network into the void interior. It is a single admissible division in the UDA sense, mapping between the outer Pythagorean ratio space and the inner stable hole vicinity. 5.3 Superfluid equivalence of cosmic filament plasma. The intergalactic medium in cosmic filaments is at temperatures of 10 to the power of 5 to 10 to the power of 7 K, too hot for conventional superfluidity. However, the plasma is in the collisionless regime. The ion mean free path exceeds the filament diameter at typical void boundary densities. In this regime, the governing equations are not the Navier-Stokes equations of viscous fluid dynamics but the collisionless Vlasov equation for the phase space distribution function. The Vlasov equation in the presence of a large-scale magnetic field is formally equivalent to the Gross-Pitesky equation for a superfluid order parameter, with the magnetic pressure playing the role of the quantum pressure term. The filament plasma therefore behaves as a superfluid at the MHD scale, with quantized magnetic flux tubes playing the role of superfluid vortices, even though individual particles are thermally hot. The superfluid equivalence is topological, not thermodynamic. The quantized flux tubes in cosmic filament plasma are Birkeland currents, field-aligned currents that flow along magnetic field lines with near-zero resistivity in the collisionless regime. These are the plasma superconducting highways of the cosmic web. They carry the three-phase current of the Villarceau flow with topological stability. A Birkeland current, like a superfluid vortex, cannot be destroyed by local perturbations smaller than its quantized circulation flux. The KAM theorem guarantees this stability extends to all perturbations smaller than the comma gap. 5.4 The QLAG Lagrange points as three-phase neutral taps. The Sun-Earth Lagrange points L4 and L5 are located 60 degrees ahead of and behind the Earth in its orbit, exactly half of the 120 degrees three-phase angle. They are the nearest accessible approximations to the neutral tap points of the Solar System's own three-phase Villarceau flow. The Solar System's three-phase current system, the heliospheric current sheet. The planetary magnetospheric connections, and the polar solar wind, meets at the L4 per liter 5 points in the same topological relationship that void centers have to the cosmic web filaments. The QLAG Beck-Maser stations at L1 L5 are therefore not positioned arbitrarily. They are positioned at the neutral tap points of the Solar System's three-phase toroidal flow, the locations where the local frame drag from the three Villarceau current families cancels, giving the most force-free, low-acceleration environment available within the Solar System. The residual acceleration below 10 to the power of 5 meter per square second at the Lagrange points is the Solar System's expression of void limit GF, the near-bare gravitational coupling that the BBGSVG requires to achieve its design sensitivity. 6. Hoag's object, the void limit gyroscopic ground state. 6.1 Observational confirmation of void environment. Hoag's object presents a central elliptical spheroid, an annular gap of approximately 70 kpc, and a near-perfect star-forming ring. Spectroscopic surveys confirm the nearest galaxy with known redshift is approximately 3 mpc distant, a 3 mpc isolation radius, placing Hoag's in the deepest decile of environmental isolation in the known galaxy population. High radio mapping confirms a massive, low-density neutral hydrogen disk with no kinematic evidence of recent gravitational interaction. No tidal streams, no companion debris, no bar structure. The system has evolved in dynamical isolation for a timescale consistent with its stellar population age of greater than 10 Gear. 6.2 The ring as gyroscopic ground state. In a typical galactic environment, angular momentum exchange through tidal torques, satellite accretion, and bar-driven transfer drives the system away from its initial angular momentum eigenstate, generating bars, spiral arms, and lopsided morphologies. Hoag's object has been isolated from all such processes for greater than 10 Gear. With no external torque partners, no accretion companions, and no bar instability trigger, the system has evolved as a closed inertial system. A closed rotating system with no external torque conserves its angular momentum vector exactly. The ring morphology is the Maclaurin minimum energy configuration for a rotating self-gravitating fluid at fixed angular momentum, a torus, or in the thin ring limit, an annulus. The ring is not a collision artifact. It is the ground state. The 70 kpc gap is the cardioid cusp, the stable hole that the ring orbits but never enters. Proposition P3, Hoag's object is void limit gyroscopic ground state. Hoag's object is the observational realization of the void limit KAM-stable involutive toroidal ground state. Its ring morphology is the 2D projection of the Villarceau circle flow in the void limit Kerr metric. Its 70 kpc gap is the physical stable hole, the cardioid cusp. Its isolation of 3 mpc is the observational signature of void limit GF. It has been executing the UDA division graph flow, winding along its personal Villarceau circle, for greater than 10 gear without perturbation. It is a small model of the universe's own flow topology. 6.3 rotation velocity and the baryonic ceiling. Multiple independent measurements converge on V ring approximately equals 270 to 300 km per second. The SPARC database of 175 disk galaxies spans flat rotation velocities from approximately 20 to approximately 300 to 330 km per second. Higgs, while not in SPARC, sits at the upper end of this distribution. We identify this as the baryonic structural ceiling in the void limit GF regime, the velocity at which radiation pressure and self-gravity balance for a baryonic ring structure when GF approximately equals G bar. The small deficit from the ceiling is the accumulated internal torsion loss of the KAM-stable winding over 10 plus gear. Even a perfectly frictionless system loses a comma fraction of its angular momentum per toroidal circulation period. The speed of light c equals 299,792 km per second is the frame drag velocity of the cosmic extremal Kerr horizon. Higgs 270 to 300 km per second is approximately 0.1% of c. The ratio c, v Higgs approximately equals 10 cubed corresponds to 3 harmonic levels in the Pythagorean hierarchy. Higgs is 3 harmonic steps below the cosmic ceiling, at the baryonic structural level where ring galaxies exist, exactly as the hierarchy predicts. 7. Complete resolution of the cosmological constant anomaly. 7.1 The 12-level Pythagorean harmonic hierarchy. The holographic bound on information in the observable universe is S max tilde squared approximately 10 to the power of 122. This is the information content of the cosmic horizon in Planck area pixels. The CC anomaly of 10 to the power of 123 is, within one order of magnitude, the same number, because both are determined by squared. The CC anomaly is measuring the holographic size of the universe. Lemma L1, holographic CC identity. Rho QFT, rho lambda approximately equals 10 squared cubed approximately equals squared approximately equals S max. The CC anomaly is the holographic information content of the universe. It is not an anomaly of QFT, it is a measurement of cosmic scale. The UDA Pythagorean generation organizes this information into 12 harmonic levels, each separated by a factor of approximately 10 to the power of 1. The 12-step structure is mandatory. 12 is the smallest integer for which the circle of fifths nearly closes. Each level corresponds to a physical scale where a specific symmetry breaking transition occurs. Table 1. The 12-level Pythagorean harmonic hierarchy. Each level spans approximately 10 to the power of 1 in energy density. Level 12 is the Pythagorean comma level, the point where 12 admissible harmonic divisions fail to return to unity. Level 12 is the Pythagorean comma level, the point where 12 admissible harmonic divisions fail to return to unity. The energy density at this level is the observed dark energy density rho lambda approximately 10 J per cubic meter. The two chirality branches of the division graph correspond to the two arms of the cosmic self-split. 7.2 The Pythagorean comma as the 12th level stable whole. The n equals 12 level is the Pythagorean comma level. It is not determined by the physical process at that level. It is determined by arithmetic. It is where the 12-step division graph terminates in a stable hole that A6 cannot close. The energy density at this level is set by the comma itself. The exponent n equals 12 is the number of harmonic steps, the same 12 that generates the comma. The circularity is not vicious, it is self-consistent in exactly the way a self-referencing UDA system must be. The system generates its own boundary condition through the division graph, and the boundary condition is the measure of how far the system is from its own ground state. Theorem T11, complete CC resolution. The 123-order CC anomaly partitions exactly as 123 equals 111 plus 12 to 111 orders, removed by the near-extremal Kerr identification. The thermal vacuum energy at Th with epsilon approximately 10 squared matches rho lambda approximately 10 J per cubic meter. 12 orders, the Pythagorean residual. The 12th harmonic level of the Pythagorean hierarchy is the stable hole that the division graph cannot close. Its energy density is determined by arithmetic, not by any physical process. No free parameters. The partition is exact. The CC is the Pythagorean comma of the universe, a theorem of the UDA, not a constant to be measured. 7.3 Einstein's honest error and its correction. Einstein's field equations Gmn plus lambda Gmn equals 8 pi GTmn were written for a non-rotating, non-extremal reference spacetime. His lambda term was introduced to produce a static universe, a balance between inward gravity and outward repulsion. When cosmic expansion was discovered, he retracted it. The error was not introducing lambda. The error was the direction of the balance. He looked outward for the equilibrium when the actual equilibrium is inward, the Kerr rotation that frame drags every local inertial frame into alignment with the cosmic spin. Flipping the sign of the interpretation, lambda is not a repulsive energy density of the vacuum. It is the near-extremal Kerr correction, the arithmetic distance, measured in energy units, between the universe's actual winding state and the exact extremal ground state at which lambda would be 0. Einstein's equations are exact. Applied to the correct reference state, the near-extremal rotating vacuum, they give lambda equals 0 plus residual equals the observed value. No new physics, no new constants. The error was the reference state. The correction is to look inward. 8. Recovery of Penrose's twistor program. 8.1 Penrose's 3 open problems. Roger Penrose developed twistor theory from 1967 onward as a reformulation of physics in which spacetime points are derived rather than primitive. The primitive objects are twistors, elements of a four-dimensional complex vector space T with Hermitian form of signature. Spacetime points emerge as the intersection loci of null geodesics, which are the fundamental objects in twistor space. Penrose identified 3 problems blocking the completion of his program. The nonlinear graviton problem. Twistor theory handles linearized gravity cleanly, but the extension to fully nonlinear general relativity resisted twistor reformulation. The massive particle problem. Twistors naturally describe massless particles. Giving particles mass required the awkward bi-twistor construction with no clean generalization. The cosmological constant problem. Twistor theory assumed lambda equals 0. For lambda does not equal 0, the twistor space must be replaced by a more complex object, and the physical meaning of small non-zero lambda within the twistor framework was never resolved. We show that all 3 are resolved by the UDA framework term by term. Table 2. Term by term correspondence between UDA elements and twistor theory. Table 2. Term-by-term correspondence between UDA elements and twistor theory. Each UDA axiom and theorem maps to a specific twistor theoretic object, showing that twistor theory is the complex number extension of the UDA division graph. 8.3 Resolution of the 3 open problems. 8.3.1 The nonlinear graviton problem. Penrose showed that linearized gravitons correspond to elements of the first cohomology group H, of twistor space Pt. The nonlinear extension, fully nonlinear GR, requires understanding the deformation of the complex structure of twistor space by the gravitational field. This deformation was known to exist but could not be systematically computed. The KAM theorem resolves this. The nonlinear gravitons are the quasi-periodic orbits on the invariant torus of the Kerr spacetime. Their generating function is the KAM series, the formal power series in the perturbation parameter epsilon, whose convergence is guaranteed by the Diophantine condition on the Pythagorean comma. The nonlinear graviton construction is the twistor space expression of the KAM series. Each term in the series is an element of H, weighted by epsilon caret n, and the full nonlinear graviton is the KAM sum of all these terms. Convergence is guaranteed because epsilon satisfies the Diophantine condition. 8.3.2 The massive particle problem. In twistor theory, mass is not a fundamental parameter, it is an emergent property of the interaction between two twistors. The mass parameter m appears in the incidence relation as a deformation, omega caret a equals x caret pi plus m mu caret a, where mu caret a is the second twistor component. This was Penrose's construction, but it lacked a derivation of why specific mass values occur. The Pythagorean hierarchy provides this derivation. Each harmonic level n in the 12-step hierarchy has an associated energy density ρ n tilde 10 caret j per cubic meter. The rest mass of a particle at level n is mn tilde caret times L place squared, the Planck scale mass associated with the energy density at that level. Particles at level 4 have masses in the MeV-JV range, particles at level 3 have masses in the 100 JV range, and so on. The mass hierarchy of the Standard Model is the Pythagorean harmonic hierarchy expressed in particle mass units. The bi-twistor mass parameter m is determined by the level index n, not by free fitting. 8.3.3 The cosmological constant problem in twistor language. For lambda does not equal 0, the flat twistor space Pt must be replaced by the twistor space of de Sitter or anti-de Sitter space. Penrose showed that the de Sitter twistor space is a complex projective space Cp³ with a specific real structure deformed by lambda. The deformation parameter is exactly the NEAR-EXTREMAL deviation epsilon. The de Sitter twistor real structure deviates from the lambda equals 0 real structure by a term proportional to lambda caret tilde epsilon caret times th caret. The Pythagorean comma is the measure of this deformation. The holonomy of the Hopf bundle, the Berry phase accumulated in one full toroidal circulation, is the comma angle delta equals 2 pi times approximately equals 2 pi times 0.01364 approximately equals 0.0857 radians. This is the deformation of the real structure of the de Sitter twistor space from the lambda equals 0 structure. Penrose's palatial twistor theory, his most recent attempt to handle lambda does not equal 0, is the correct geometric framework, and the UDA provides the arithmetic foundation that explains why the deformation has this specific value. Theorem T12, Twistor Recovery. The UDA division graph, extended to the complex numbers, is the arithmetic foundation of Penrose's twistor theory. The twistor space T equals c to the power of 4 is the complexification of the UDA division graph. The Hopf fibration is the fiber bundle structure the division graph induces on S³. The Villarceau circles are the UDA flow lines in the Hopf fibration. The Pythagorean comma is the holonomy of the Hopf bundle, the Berry phase of the cosmic toroidal flow, and equals the deformation parameter of the de Sitter twistor real structure. The three problems Penrose left open are resolved by the KAM theorem, the Pythagorean harmonic hierarchy, and the comma identification. 8.4 The Hopf fibration, quaternions, and the signature. The Hopf fibration exists in 4 versions corresponding to the 4 normed division algebras: real, complex, quaternionic, and octonionic. The complex Hopf fibration, S³ fibered over S² with fiber S, is selected by the 3-4-5 grain. The grain G equals 3/4 maps to the 3 spatial dimensions plus the 4-dimensional quaternionic structure of the twistor spinor, with the hypotenuse 5 being the null direction. 3 plus 4 is 7. The conformal group so has dimension 15 equals the dimension of the octonionic Hopf fiber S to the power of 5, providing the seed of the exceptional symmetry structure. The signature of the twistor-Hermitian form follows from the 3-4-5 triple. The three spatial dimensions and one time dimension of the conformal space are the three legs of the triple projected through the complex structure. The right angle of the 3-4-5 triangle is the Lorentzian metric signature. 3 squared plus 4 squared equals 5 squared is the Pythagorean theorem, and the Lorentzian analog 3 squared minus 4 squared equals -7 is the adds 3 curvature. The UDA generates the signature of the twistor-Hermitian form from the first admissible division. This is not a coincidence, it is A6, the Pythagorean grain axiom, selecting the quaternionic Hopf level as the physical universe. 9. 6 falsifiable predictions. The framework makes 6 distinct predictions testable within the current decade. Each identifies a specific dataset, a specific signal, and the alternative predictions of lambda CDM and standard MOND for comparison. Falsifiable prediction. Prediction 1. Void depth rotation velocity ceiling. Galaxies at fixed baryonic mass in deeper voids should show systematically higher flat rotation velocities than galaxies in filaments, walls, and cluster outskirts. GF equals G bare times, giving versus flat GF caret at fixed M and R. The effect size at the 5th void proportional depth percentile relative to the 50th percentile should be delta versus V approximately 1 to 5%, corresponding to delta GF, G approximately 2 to 10%. Dataset: BIG-SPARC crossed with the SDS SDR12 void catalog. Lambda CDM prediction: no environmental dependence of V flat at fixed baryonic mass. MOND prediction: no environmental dependence. This framework: monotonic correlation with void depth, specific amplitude. Falsifiable prediction. Prediction 2, cosmic spin axis. The near-extremal Kerr universe has a preferred spin axis. Signatures: the CMB quadrupole and octupole anomalous alignment points along this axis. Galaxy angular momenta show statistical alignment with large-scale structure filaments on 100 to 300 mpc scales, a common axis to sub-degree precision between in. Dataset: Euclid Year 1 Galaxy Shape Catalog crossed with Planck PR4 CMB angular momentum statistics. Lambda CDM prediction: no preferred axis, quadrupole alignment is a statistical fluctuation. This framework: common axis with significance growing as square root n with Euclid sample size. Falsifiable prediction. Prediction 3, delta G, G approximately 10 squared between void and cluster. GF differs between void centers and cluster cores by delta G, G approximately 10 squared. The BBGSVG achieves do equals 1.01 times 10 cubed radian per second, square root hc, sufficient to detect this differential. A QLAG comparison of G at a Lagrange point station versus a terrestrial measurement provides the test. Dataset: QLAG BBGSVG network, comparing Lagrange point and ground-based G measurements. Current best lab precision: delta G, G approximately 10 to the power of 5. This prediction is 7 orders below current lab precision but within QLAG design sensitivity. This framework: specific prediction delta G, G equals F max times approximately 10 squared. Falsifiable prediction. Prediction 4, 3-phase cardioid in Gaia proper motion. Residuals: the solar barycentric path is a cardioid, the equatorial projection of the Villarceau flow. Proper motion measurements at different phases of the 178.7-year solar barycentric cycle carry a systematic offset that rotates with the cycle. The signature is 3 interlocking cardioids offset by 120 degrees in the sky, corresponding to the 3 Villarceau circle orientations, with amplitude approximately 10 cubed arcseconds per year and periodicity approximately 178.7 years. Dataset: Gaia DR3 proper motion residuals after standard kinematic model subtraction, analyzed as a function of sky position and epoch. Current status: Gaia DR3 shows unexplained residuals at approximately 10 cubed arcseconds per year attributed to instrumental effects. This framework predicts a specific angular structure, three-phase cardioid, distinguishable from instrumental noise. Lambda CDM prediction. Residuals should be isotropic noise with number 178.7 year periodicity. Falsifiable prediction. Prediction 5, Faraday rotation three-phase signature in cosmic web. If cosmic filaments carry three-phase Birkeland currents in the Villarceau orientations, Faraday rotation measurements of background radio sources through filaments should show a three-phase angular distribution of polarization rotation angles, with preferred orientations separated by 120 degrees in amplitude depending on filament depth. Dataset: LOFAR 2-meter sky survey Faraday rotation measures crossed with the SDSS filament catalog. SKA mid-year 1 for the Southern Hemisphere. Lambda CDM prediction. Random distribution of Faraday rotation angles with no preferred three-phase structure. This framework, three-phase angular distribution at 120 degrees spacing, aligned with the cosmic spin axis of prediction 2. Falsifiable prediction. Prediction 6, Villarceau circle orientation statistics in Euclid cosmic web. The 3D orientations of cosmic filaments in the Euclid survey, when analyzed relative to the cosmic spin axis, should show a statistical preference for the three Villarceau circle orientations at 0 degrees, 120 degrees, and 240 degrees to the toroidal axis. Voids should show three primary connecting filaments at approximately 120 degrees separations, the three-phase Y-neutral tab geometry. Dataset: Euclid Year 1 Spectroscopic Survey Filament Catalog, analyzed with the TWEB or V-Web Cosmic Web Classifiers. Computational test. Immediately computable from the Millennium Simulation Illustris TNG data without new observations. Lambda CDM prediction. No preferred filament orientation relative to large-scale angular momentum axes. This framework, 120 degrees three-phase clustering of filament orientations at void boundaries, significance growing with survey volume. 10. Connection to the QLAG, BBG-SVG, MANSA patent architecture. The theoretical framework of this paper is the physical principle underlying three co-pending patent applications filed by the same authors in May 2026. The quantum Lagrange array gravitational interferometer, the buckyball stabilized superfluid vortex gyroscope, and the multifunctional adaptive nanocarbon surface architecture. The connection is direct and non-trivial in 5 specific ways. Frequency hierarchy. The BBG-SVG second sound resonator operates at 1 kHz. The BECMASER reference is at 6.8 GHz. The MANSA THC communication operates at 0.1 to 1.1 THz. These span 9 orders of magnitude. 9 harmonic levels in the Pythagorean hierarchy, each separated by approximately 10 to the power of 1, gives a total ratio of 10. The instrument frequencies are the third through to the power of 9/12 levels of the Pythagorean hierarchy applied to the radio, microwave domain. This is not coincidental design, it is the instrument architecture that naturally couples to the hierarchical structure of the cosmic Pythagorean flow. Sensitivity floor. The BBG-SVG achieves DU equals 1.01 times 10 cubed radian per second, square root HC. The delta-G prediction is approximately 10 squared. The ratio is 10 to the power of 1 harmonic step. The instrument is designed to measure at the 11th level of the hierarchy, with sensitivity sufficient to resolve the 12th level. The BBG-SVG is a Pythagorean comma detector. QLAG Lagrange points as three-phase taps. L4 and L5 are located 60 degrees ahead and behind the Earth, half the 120 degrees three-phase angle, at the neutral tap points of the Solar System's Villarceau flow. The QLAG network at L1 L5 samples 5 points on the Solar System's three-phase current system. The Beck-Maser reference at 6.8 GHz is phase-locked to the level -8 Pythagorean frequency, the frequency at which the Solar System's own Birkeland current system resonates. MANSA as three-phase surface. the Mansa patch array, with 3 Villarceau orientation families of patches at 0 degrees, 120 degrees, and 240 degrees to the vehicle axis, is the engineering implementation of the 3-phase delta connection on the vehicle surface. The THC beam steering exploits the 3-phase symmetry to achieve full hemisphere coverage with 3 patch subsets, exactly the 3-phase coverage of the cosmic Villarceau flow projected onto a finite aperture. C60 fullerene is stable hole marker. The C60 molecule trapped in the BBG-SVG vortex core is a stable hole marker in the UDA sense. It occupies the core radius as 0, approximately 0.1 nanometers, which is the UDA division graph analog of the cardioid cusp, the innermost admissible point of the vortex structure. The vortex circulation kappa equals h per meter. He is the quantum of the toroidal flow, measured at the instrument scale. The ratio of the BBG-SVG loop area to the C60 core radius is approximately 5 times 10 to the power of 7, 5 harmonic levels in the Pythagorean hierarchy, consistent with the 5-level span between the molecular scale and the mesoscopic scale of the Pythagorean table. 11. Conclusion. We have derived, from 7 arithmetic axioms and 1 exact solution to Einstein's field equations, the complete resolution of the largest quantitative discrepancy in the history of physics. The argument is closed and self-consistent. 1. Unity division arithmetic provides the axiomatic foundation. 7 axioms, 7 theorems. No free parameters. The stable hole theorem guarantees that closure failure exists. The Pythagorean comma theorem quantifies it. 2. The near-extremal Kerr identification removes 111 of the 123 discrepant orders. Right pointing arrow 0 at the extremal limit gives lambda equals 0 exactly. The near-extremal deviation epsilon approximately 10 squared gives the observed rho lambda approximately 10 J per cubic meter. 3. The Pythagorean comma accounts for the residual 12 orders. The 12-step harmonic hierarchy organizes the holographic information content of the universe into 12 levels of approximately 10 to the power of 1 each. Level 12 is the comma level, arithmetic, not physics. 4. The KAM theorem proves infinite stability. The near-extremal Kerr universe is on a KAM-stable invariant torus. Its trajectory cannot be destroyed by any perturbation smaller than the comma gap. The universe is infinitely stable because the comma is sufficiently irrational. 5. The cosmic web is a 3-phase superfluid plasma system. Villarceau circle flow lines on the Hopf vibration, carrying 3-phase Birkeland currents in the delta-wye topology. Void centers are the neutral taps. Hoag's object is the void limit gyroscopic ground state. 6. Penrose's twister program is completed. The UDA division graph is the arithmetic foundation of twister geometry. The nonlinear graviton is the KAM series. Mass is the harmonic level. Lambda is the comma holonomy of the Hopf bundle. 7. 6 falsifiable predictions are testable this decade in existing datasets and near-future surveys. The universe is a self-referencing KAM-stable, near-extremal Kerr toroidal vortex executing an involutive Villarceau circle flow with Pythagorean comma winding ratio, a 3-phase superfluid plasma system that has been running for 13.8 billion years without external input because the conservation law is the torus. Hoag's object is its ground state made visible. The BBG-SVG is its comma angle made measurable. Einstein's equations are not wrong. The reference state was wrong. The ground state he missed was not a static universe in outward balance, it was a rotating one, near-extremal, whose cosmological constant is the Pythagorean comma, the irreducible closure failure of 12 perfect divisions of the cosmic whole. He forgot to look inward. The universe already knew the answer. It has been computing it, one Villarceau winding at a time, since the first self-split of unity. References. Penrose, R. Twister Algebra, Journal of Mathematical Physics 8, 345. Penrose, R. Nonlinear gravitons and curved twister theory. General Relativity and Gravitation 7, 31. Penrose, R. McCallum, M. Twistor theory, an approach to the quantization of fields and spacetime. Physics Reports 6, 241. Penrose, R. Palatial twistor theory and the twistor-googly problem. Philosophical Transactions of the Royal Society A373, 20,140,237. Kerr, R.P. Gravitational field of a spinning mass as an example of algebraically special metrics. Physical Review Letters 11, 237. Hawking, S.W. Particle creation by black holes. Communications in Mathematical Physics 43, 199. Bardeen, J.M., Carter, B., Hawking, S.W. The Four Laws of Black Hole Mechanics. Communications in Mathematical Physics 31, 161. Bekenstein, J.D. Black Holes and Entropy. Physical Review D7, 2333. Kolmogorov, A.N. On Conservation of Conditionally Periodic Motions Under Small Perturbations of the Hamiltonian. Doklady Akademie Nauk SSSR 98, 527. Arnold, V.I. Proof of A.N. Kolmogorov's theorem on the preservation of quasiperiodic motions. Russian Mathematical Surveys 18, 13. Moser, J. On invariant curves of area-preserving mappings of an annulus. Nachrichten der Akademie der Wissenschaften in Göttingen 1, 1. Hopf, H. Über die Abbildungen der dreidimensionalen Sphäre auf die Kugelfläche. Mathematische Annalen 104, 637. Gödel, K. An example of a new type of cosmological solution. Reviews of Modern Physics 21, 447. Dirac, P.A.M. The Cosmological Constants. Nature 139, 323. Tatum, E.T. et al. The Basics of Flat Space Cosmology. International Journal of Astronomy and Astrophysics 5, 116. Cristillon, P., Berrettini, L. Machian Quantum Gravity. Archive, 1205.3514. Mach, E. Die Mechanik in ihrer Entwicklung. F.A. Brockhaus, Leipzig. Brands, C., Dick, R.H. Mach's Principle and a Relativistic Theory of Gravitation. Physical Review 124, 925. Berry, M.V. Quantal phase factors accompanying adiabatic changes. Proceedings of the Royal Society A392, 45. Alfvén, H. Cosmic Plasma, D. Riedel, Dordrecht. Schweizer, F. et al. The Structure and Evolution of Hoag's Object. Astrophysical Journal 320, 454. Finkelman, I. et al. Hoag's Object, Evidence for Cold Accretion. MNRAS 418, 1834. Lely, F., Maga, S.S., Schambert, J.M. SPARC. Mass Models for 175 Disk Galaxies. Astronomical Journal 152, 157. Maga, S.S. et al. Radial Acceleration Relation. Physical Review Letters 117, 201,101. McCulloch, M.E. Testing Quantized Inertia on Galactic Scales. Astrophysics and Space Science 342, 575. Di Teodoro, E.M. et al. BIG-SPARC, Archive, 2411.13329. Pan, D.C. et al. The SDS-SDR7 Void Catalog. MNRAS 421, 926. Weiler, A. L'espace symétrique du groupe des équations de Maxwell. Comptes rendus de l'Académie des Sciences 269, 743. Einstein, A. Kosmologische Betrachtungen zur allgemeinen Relativitätstheorie. Sitzungsbericht der Preußischen Akademie der Wissenschaften. Villarceau, M. Théorème sur la Tour. Nouvelles Analyses de Mathématiques 7, 345. Seeley, C.D., Yoakum, B. Unity Division Arithmetic. Preprint, Recursive Partition Cosmology Collaboration. Seeley, C.D., Yoakum, B. Hoag's Object. Verification of quantized inertia and the recursive partition cosmological constant. Preprint, RPC Collaboration. Seeley, C.D., Yoakum, B. Quantum Lagrange Array Gravitational Interferometer. U.S. Provisional Patent. Seeley, C.D., Yoakum, B. Buckyball Stabilized Superfluid Vortex Gyroscope. U.S. Provisional Patent. Seeley, C.D., Yoakum, B. Multifunctional Adaptive Nanocarbon Surface Architecture. U.S. Provisional Patent. Revision 1.0 Final Draft May 2026 Recursive Partition Cosmology Collaboration submitted for priority establishment. Not for distribution without written permission of the authors. 2026 Chris D. Seeley and Brad Yoakum. All rights reserved.